Hi, I'm Ziyang from Syracuse University, and I'm here to share our exciting work in progress about generating realistic Brier distributions for SSDs. As you already know, SSDs have gained significant popularity in the past years, both commercially and academically, and a variety of SSD development platforms exist today to meet the research demands in improving and understanding SSD performance. More recently, however, fail-slow symptoms have become prominent, where the bit error rate caused by the wear out decreases the performance of the drive. Thus, to understand the fail-slow symptoms, it is imperative that SSD should be studied at an edge state. However, reaching a realistic edge state is difficult, and we currently don't have any SSD aging tools available. One could consider using preconditioning to artificially edge the device, but it is not the original purpose of preconditioning. Preconditioning is meant to prepare the SSD into a steady state, and using it to edge the drive would be prohibitively expensive. Essentially, to reach an edge state with 3 years, one must first run 3 years worth of workloads, both costly in terms of resources and time. So our approach to this challenging is a machine learning-based SSD aging framework that generates representative future VR states based on workload sampling. However, using machine learning to make both faster and accurate prediction is challenging. First, the inference must be fast relative to the simulation time, as reducing the overall time to reach an edge state is the very purpose. Thus, using complex deep learning models may end up slowing down the aging process. Second, the inference must be accurate, but the complexity of modern SSDs makes this difficult. Any SSD internal activities can increase the wear, which in turn increases the error rate, which feedbacks into the increased SSD internal activities to handle errors. These complex interdependencies must be correctly modeled to infer the future wear state. We approach by incrementally building a lightweight regression model for each block to capture the changes in SSD internal states and predict the trajectory for blocks wear out using the information from the past. More specifically, our generative process works in 3 stages. First, we use actual simulation during a workload sample to observe SSD's internal activities and capture the changes in the SSD internal states and collect the information that will later be used for prediction. Once enough workload has been sampled, we use the gathered data to build a lightweight regression model to predict the future state. Finally, these generated future states are fed back into the simulation, where it will continue to run and sample workloads. And these stages will repeat until the device reaches its desired age. We compare our work against 2 prior works that use machine learning to accelerate simulations. At a high level, DVS considers multiple model candidates, but the model is not always updated before each prediction stage. On the other hand, CML continuously incorporates the latest data to update its model. And we use FTL Sim to configure a 256 GB SSD and run 3 different real-world workloads. The solid line is the USENIX distribution when the simulator is continuously run, serving as the baseline to the ML-based simulators. The blue dotted line is our approach that runs for 2 units of the time and predicts the state 1 unit of the time into the future. Essentially, we accelerate the simulation by 33% with this workload sampling configuration. As we can see, our predicted distribution closely follows the fully simulated result. On the other hand, DVS and CML don't closely match the black solid line, indicating high inaccuracy in predicting future state. Moving forward, we are investigating how to make the ML results more explainable, and we start by analyzing the behavior of our work across more workloads. And our approach is modular, and we also plan to integrate our work into more platforms such as Amber and FEMU. Lastly, while there is an inherent trade-off between prediction accuracy and efficiency, we are going to explore the optimal point along this trade-off. Thank you.